Hello, it's me, and it's time to pull some puzzles out of the cupboard, things I haven't been able to get to for a little while, and look at this thing called the Icosamate. So you had the fortune and yet misfortune of picking this up maybe from the HK Now store. I say fortune because it is really a nice little puzzle. Misfortune because, you know, honestly, the HK Now version of it is rather, I think, kind of sloppily made. I actually had it, used it, solved it, and then the whole thing came apart on me to the point that I could not put it back together. Now, I'm not the best assembler to begin with, but this was impossible. And this was back when they had the original color. But in any case, this comes from Raphael, so I figured I'd get it done by somebody who really knows what they're doing. However, you may have a different experience. It is definitely worth getting because it is a very fun solve. So that's what we're gonna go through. Now, what I'm gonna do is kind of go through what this puzzle really means and some of the strategies. I'll put a little timestamp in terms of when the actual scramble and solve begins, if you'd like to skip to that. But for some people, they want me to go a little slower so I can explain some of the concepts so they can actually start pausing the video and try to do it themselves. So I'm going to start by that, seeing if I can arm you with that. So on the face of it, no pun intended, this is really a shape mod of a pentultimate. And a pentultimate, in turn, is really just kind of a shroud kind of a puzzle. It's a shroud where underneath you have a combination of a kilominx and a crystal pyraminx. You can see it a little bit more over here. Inside this is a bandaged crystal pyraminx along with the kilominx. So you can see it moving over here. This looks exactly the same on the inside, but you have these outer shell that surrounds it, and that's really what a pentultimate is. It's a deep cutting, face turning dodecahedron, but again, it's really more of a two-layer dodecahedron of a kilominx combined by a crystal pyraminx that has this capsule basically around it, and it's the capsule that you're solving, while the crystal pyraminx is left to just do what it's doing. Unless you have this particular puzzle, in which case you can solve all of it. And I do have a tutorial on that. So I also have a tutorial on the pentultimate, so that should help with this. But there are a couple of differences. First off, these centers here are monochromatic. They're one color, so that means it has rotational symmetry or rotational equivalency. So it's got 5 sides to it, and each rotation, each conformation is exactly the same. The equivalent on the Icosamate is this guy over here, and you can see that every color is different. So as I turn this, the rotation actually means something. The rotation matters. And that's where people, I find, are getting into the most problems with this. That's where I get a lot of messages as to what to do when one center is rotated, which is not a problem here. But there is a positive trade-off, an easier trade-off, where the corners here actually, yeah, so these look like corners over here, but they're actually centers just like this. These corners here are 3-colored, and this is 1-colored. So one of the algorithms that are used, I have to make sure that the orientation is correct with this in order to do the exchange. Here you don't. So this has equivalency here. Whereas the center does have equivalency and it doesn't over here. So those are the main differences. And just to go over the algorithms real quick, there was an algorithm whereby you swapped these two, the centers, which also swapped these two centers over here. So if you went down, down, up, up, it swapped these two, but it also swapped these two. Down, down, up, up. And you'll find it's exactly the same thing here. So we're going to hold a center in front of us and a center right at the top. We can start off with the right side counterclockwise down, and then down, up, up. It swapped these two, but also swapped these two. We'll just get it back, down, down, up, up. The only other algorithm to know, and that's more of a commutator than an algorithm, is the one that flip-flopped these guys. So these corners over here exchanged, and what that algorithm was, where this color will end up here and this color will end up here, is we go down, 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 up, 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 up. We do that 3 times. So that was 1 time, 2 times, down, 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 up, 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 that's 2, and finally 3, down, 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 up, 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 up. So what you can see is everything is the same, but you just flip-flop these guys. Now remember, when I did the tutorial, I had to orient this in such a way so that I can make sure that the colors are properly placed, otherwise it's going to end up in the wrong place. And when you do your down, down, it's 1, 2. So I think you could surmise that. So down, down, 1, 1, 1, 1, 1, 1, 1, 1, 2, 2, 2, 2, 2, 2, 2, 2, 3, 3, 3, 3, 3, 3, and 3, 3. Okay, so if we were to do the same thing here, we have to make it make sense to us. This is here, it's going to exchange with this guy. So the way that we orient it is we have one of the centers right in front of us, and this will exchange with this guy over here. So we'll go down, 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 up, up. Remember to do it 2, up, up. So it's 1, 1, 1, or rather 2, 2, 2, 2, 2, 2, 2, 2, and once more 3, 3, 3, 3, 3, 3, 3, 3. Okay, so it did exchange these two. Now I forgot to tell you something. It not only exchanges these two, it also exchanges these two. And if I had shown it, you would have seen that these two exchanged, but also these two exchanged. So my apologies, I forgot to point that out, but that is a very important part of this algorithm. Now, once again, as pointed out, you don't have to worry about orientation. You have rotational equivalence, so it doesn't really matter what rotation that's in. And that makes it easier than here, where I always had to keep shifting and changing things until I got the right rotation. So to get it back, 1, 1, 1, 1, 1, 1, 1, 1, 2, 2, 2, 2, 2, 2, 2, 2, 3, 3, 3, 3, 3, 3, 3, 3. Okay, so remember, it exchanged this one, and if you go past these two to get to this center over here, which is actually a corner, I guess, these two will exchange, and then if you go past these two centers here, these two will exchange. This one isn't even touched. Okay, so those are the two algorithms, but there's one more thing to bear in mind, and this is going to get you through that last step. Now, I'm not going to tell you what it is until I get there, but I am going to point something out. Something that might seem a little esoteric, but actually has importance in terms of what it comes to in terms of solving the puzzle. So when I describe to people how to solve something simple like a 2x2, if I see somebody struggling with it and I say, hey, it's just a trick, I can show you how to do it, there is a step that I show that really impresses them. They're shocked to see it. And that has to do with a mathematical principle of how these puzzles are solved. Now, by mathematical principle, I don't really mean like equations and things like that. I mean the geometric transformation in space and time of a shape. So what I mean by that is how it changes. So some people are more, let's just say, procedural oriented in their brains, where they like algorithms, they like numbers, they like to crunch numbers. Some of them are more spatially oriented, where they like the shape of things. They like how things translate through space and time. And that's what twisty puzzlers like, is they enjoy math, but they don't necessarily like the number aspect of it, some anyway. They more like how things sort of declare themselves in a geometric position in space and time, and how it twists and turns, and how the numbers and the math comes out in terms of the spatial orientation. So at its very simple concept, we'll note that we have 1, 2, 3, 4 colors in this plane, right? So in its simplest form, I can take a puzzle like this and just do a very simple move like this. Boom. So as you can see, what I did by doing that one rotation is I changed the conformation a little bit. It still looks like a cube, but it's a different color in front of me. Now if I have 1, 2, 3, 4 colors, if I do the same move 4 times, it'll render me right back to where I started. So we'll do this move, 1, 2, 3, and 4. Now you're probably thinking, well, yeah, so what? What possible bits of wisdom can I get from that? But what it really means is that by doing a certain movement, doing a certain conformation, by knowing the number of sides that we have, the number of colors within that plane that you're moving, I can predict that I can get the puzzle right back to its original position. So let's take a look at a more expanded version of a move. That was just a very simple move, right? Just turning it counterclockwise. Well, what if I added a commutator where I did a specific pattern of moves like RI, DI, RD? So a commutator is you take a move, two moves, and you undo those two moves. And what it does is it puts your piece somewhere in another conformation, in another place around the puzzle. Then you do that again, it'll put it back to its original place, but in a rotated state. For instance, we'll go RI, DI, and then reverse it RD. It took this piece, put it down here, right? Now if I do it again, it'll pop it back up, RI, DI, RD. So here it is popped back up, but you notice something a little off. It's rotated wrong. So what this commutator did is it basically was sort of like going like that. What I did is a more complex move where I only affected a piece here that I'm concerned with, and it brought it down and brought it back up, but in a rotated way. Now, it did some things to the bottom here, seemed to mess it up, but it's actually in a very specific conformation. Now, just like it had 4 colors on one plane, this piece has 3 colors, which means if I do that commutator, which is bringing it down and back up again, and I do that 3 times, it will return this back to its original state, including the entire puzzle. So every other piece that has to do with the piece that I'm moving, if it's the same piece, will return back to its original conformation. So that was one use of that expanded commutator. Now let's do the second one, RI, DI, RD, and then again to complete the second one, because I moved it down here, RI, DI, RD. So you can see it's back up here, but in a different rotated position. So if I do the number of that entire commutator, the number of, the same number of colors that I have of that particular corner, it'll return it back to its original conformation. So a third time will be RI, DI, RD, RI, DI, RD, and you can see it's returned back. Now, to you experienced solvers, that might seem, well, yeah, that goes without saying, I understand that. But I've got 2 things to say to that. First off, to those that you're teaching this, that's like an extraordinary thing. They look at that and they're like, wow, that's very, very impressive. I didn't know that. But if you are actually having a hard time with a conformation, the rotation of the final piece that everything is in except one center here is rotated wrong, you may understand what I'm talking about, but you don't understand it enough to really broadly apply it. Because if you did understand it, that would not be a problem. So the fact that it is means that there's something about that concept that isn't quite completely ringing true. So long story short, if you have a piece, the number of colors will tell you how many times to do that algorithm before it returns back to its original conformation. Now, let's extend that concept a little bit further and say that when you do that commutator 3 times, now I don't just mean the RIDARD, I mean doing it twice, RIDARD, RIDARD, because it brings it down and back up again, the bottom portion doesn't care what happens to the top portion. So let's do it once again, RIDIRD, RIDIRD. It brought this up, this seems to be all messed up. But notice that the only thing that's different on the top is the rotation of this piece. This has all the same pieces on the bottom. So if I move this to here, and I do that RIDARD 2 more times, the bottom doesn't care what happens to the top. This will return back to its original position. This won't, because this is already taken out of the picture, and so this is already off, and now this will be off, having been rotated twice. So I'll do it once, RIDIRD, RIDIRD, so that's once. Now I can either do it again here, or I can move this into position and do that once, because it'll be a total of 3 times. I did this once, and I can do this once. Or I can move this back here, and that'll be this once, and I'll do this one twice, RIDIRD, RIDIRD. Now what you notice is that these are taken out because I isolated this, but the bottom returned right back to its original conformation, and it did that because all it cared about is doing that algorithm 3 times. Doing that quick double commutator, so to speak, 3 times. But what I had to do is I couldn't move the bottom, I just could move the top. So basically, this is a situation that everybody runs into when they're doing a 2x2, is you have everything in, but you have these 2 that are out, right? I mean, they're not out, they're in where they need to be, but they're not rotated correctly. So just the way the mathematics works on this puzzle, the parity of this puzzle, is by doing the RIDARD 3 times. Well, the way this works is it's got to be a total number of 3. because that's the only way that this is going to work. So when you're in this position, you just think, all right, we'll do RIDA, RD until this is rotated correctly. RIDA, RD, RIDA, RD, RIDA, RD, RIDA, RD. Now if you're counting, you notice I did that 2 times. This seems to be messed up, but I just moved this into place. And now I know because this was 2, this has to be 1 more time for the 3rd time. RIDA, RD, RIDA, RD, and well, it solves the rest of the puzzle. So here's the whole point of that. The point is that you can count the number of independent colors to see how many times a commutator will return you back to its original conformation, including the bottom of the puzzle, and that the total number of rotations that every one of these pieces has to do has to equal to 3 in order to bring it back. Now that's going to be important because rotating this piece, if this is rotated wrong, could be an issue. What we're going to have to do is get this into its normal configuration and let these pieces be rotated wrong, because then I can do an equivalent RIDA, RD to get all these back. Now the question that I have for you is how many times would I have to do a similar RIDA, RD in this puzzle to get it back to its original conformation? Well, how many do you think? Stare at it for a little while. Tell me what you think. Pause the puzzle. What number did you come out with? Well, the number you should have come out with is by counting these colors here on each piece. So if these represent corners just like this, you counted 1, 2, 3, 4, 5. I should do 5 RIDA, RDs to get them all back to the same position. Which means if 2 or 3 of these are rotated wrong, then the total amount of rotation that'll have to be done is 5. You'll have to do RIDA, RD, say 3 over here and then 2 over here. The bottom will go right back to its original conformation and these will be rotated in. If that number is not 5, you've got something of a, well, maybe a parity problem or a placement problem or a rotation problem. So that might not make a whole lot of sense if you've not solved this yet, but to those who struggle with the final positioning of the centers should know exactly what I mean. Now what do I mean by RIDA, RD? Well, if you put this in front of you and this is your center, you're going to be moving this down and to the right. That's going to be your RI. Now your bottom is going to be here. This is your D move. And that's because this is really a 2-layer puzzle, so that's the bottom over here. So to move this down here, RI, and then you go DI here, then RD, and then do it again to bring this back up, RI, DI, RD. So you have to coordinate an RID, RD where this is brought down and then can be brought back up. So you can see this is brought back up, but it's rotated wrong. Now my first RI was a clockwise rotation, and that clockwise rotation basically made this rotate counterclockwise. Now you can see the bottom seems to be somewhat messed up, these two. Well, let's do that 5 times and see what happens. 2, 2, 2, 2, 2, 2, 2, 2. Back up, this is now rotated over here. 3, 3, 3, 3, 3, 3, 3, 3. This is now rotated down here. 4, 4, 4, 4, 4, 4, 4, 4. Now it's rotated here. Now, by the way, I have one more rotation to get it back. I could just move this into place over here, and if I did that one more time, this bottom will return right back to normal, but I'll have 2 that are rotated out. I could do that. We'll go RI, DI, RD, RI, DI, RD. So what you're going to find is this is back, and the bottom has returned back these centers anyway. These have been messed up. Now you may say, well, it didn't go back to the beginning conformation, and that's true, but that's only because these are sort of their own independent pieces. These actually have been, these actually move in a more complex way. So if I keep doing that over and over and over again, eventually these will go back into its original configuration, but the complexity of these movements are more. So basically this went to here, these two flip-flopped. If you can see that these two flip-flopped, these two flip-flopped, and this light green one went to here. These two flip-flopped and these two flip-flopped. So that's a whole lot of flip-flopping. So let's see what happens if we do it again. 5 times. RI, DI, RD, 1, 1, 1, 1, 2, 2, 2, 2, 2, 2, 2, 2, 3, 3, 3, 3, 3, 3, 3, 3, 4, 4, 4, 4, 4, 4, 4, 4, and finally 5, 5, 5, 5, 5, 5, 5, 5. Okay, so it all came back to where it was, and that just meant that these had a little bit more complexity. You caused a bunch of swapping. I think we in all swapped maybe 4 or 5 different pieces together. But that's the fun of these puzzles. That's the mathematical concept behind them, is this symmetry in motion and how it plays out. Because what you're looking for is complete knowledge of where things are going to go, predictability with what's going to happen with the puzzle. So, with that said, let's go ahead and scramble it and see how we can work through strategies on how to solve it. Now, I know how the mass-produced version turns, and it's not bad. It doesn't turn bad, but it got to a point where it kept getting into a sticky point, then more of a sticky point, and then it just completely was not able to move. It got stuck, so I tried to gently coax it and persuade it. It was not into that at all, so I had to force it a little bit, and then the whole thing popped. I contacted the HK Now store where it came from, and they had offered a lot of advice on how to reassemble it. Then I convinced them that there was a piece that was broken. They offered to send another piece, so they did the best that they could, but I just think that the model of the puzzle wasn't all that good. Okay. Now, I was considering maybe scrambling the pentultimate along with that, but I think we're just going to look at this puzzle for what it is right now. You can take a look at the pentultimate tutorial to see if there's any questions on that, but I'm going to look at this now as its own entity, because I've got a lot of other Raphael Elite versions of this to solve. Okay, so with that said, here you have a very symmetric and beautiful looking scrambled Icosamate.